Hi and welcome to another lesson in the physics video series. Today we're going to work on inelastic collision problems using the conservation of momentum. Alright, let's get started. In this problem, we see that a 1 kilogram cart moving with a speed of 0.5 meters per second on a horizontal surface collides with the 1 kilogram cart initially at rest. The carts lock together. What is the speed of the combined carts after the collision? So we notice that mass 1 and mass 2 are identical, and this is the situation that I showed you in the last video, that when m1 equals m2, the final speed of both carts is half of the impact speed of v1. v1 happens to be 0.5 meters per second, and the answer could then be chosen as 0.25 meters per second. But let's show you how to calculate that. Starting with momentum before equals momentum after. Each cart gets its own momentum expression. Since there are two carts, there are two masses, m1v1 plus m2v2. The momentum of each cart before the collision is equal to the momentum of each cart after the collision, m1v1 prime plus m2v2 prime. The question asks for the speed of the combined carts. The fact that the carts are combined means that you are dealing with an inelastic collision. You're conserving momentum, but not kinetic energy. And even though we haven't discussed kinetic energy, we can say this much so far. If there is a decrease in speed after the collision, you have lost kinetic energy. Let's take a look at the math. m1v1, 1 kilogram times 5 meters per second, plus m2v2, 1 kilogram times 0 meters per second, equals m1 v1 prime plus m2 v2 prime. Now we know that m1 and m2 are the same mass of 1 kilogram, and we know that v1 prime and v2 prime are the same speed, which gets factored out. So they added the masses and they factored out the v. And then of course, continuing in the carry down, we solve and we get v prime, the final speed of the combined carts, equals 0.25 meters per second, which is in fact half of the initial impact speed of mass 1 against mass 2. This is consistent with the results that we've seen from our general derivation. Let me show you. Recall in the last video we used this expression, v equals the mass ratio of v1, m1 over m1 plus m2, and when the masses were the same, 1 m1 over 2 m1, you get a 1/2 ratio. The final speed of our equal masses is equal to half of the impact velocity of mass 1. And that is what we have here in this expression. The speed of the combined carts after impact is equal to 0.25 meters per second, which is exactly half of v1, which was 0.5 meters per second. In this next problem, a 3 kilogram steel block is at rest on a frictionless horizontal surface. A 1 kilogram lump of clay is propelled horizontally at 6 meters per second towards the block as shown in the diagram. Upon collision, the clay and the steel block stick together and move to the right with a speed of, and that's what you have to find. This problem is exactly like the last inelastic question we solved, and we have mass 1 of 1 kilogram, speed 1 of 6 meters per second, mass 2 of 3 kilograms, with its initial speed at rest. So the clay hits the block, they move off together. This is exactly the same solution, and you could see that this is a 1-to-3 ratio. A 1 kilogram to 3 kilogram ratio, light hits heavy. Intuitively you should know that when light hits heavy, they will move off together, but at a much slower speed, and the fraction you can see, it will be 1/4 of the original speed of v1. Here you can remind yourself that this is something we solved in the last video. When you have a 3-to-1 mass ratio, light hits heavy, the final speed is 1/4 of the original impact speed. Let's take a look at this on the simulation. I have the red car at 1 kilogram, the blue car is at 3 kilograms. I have the initial velocity of mass 1, v1 set to 6 meters per second, and the blue car v2 will be at rest. Let's run the simulation. So we can see that both cars move off together at 1.5 meters per second, which is 1/4 the speed of 6 meters per second. Let's prove that in the math. And so we use the conservation of momentum. Momentum before equals momentum after. m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime, but v1 prime and v2 prime are the same, factoring them out as v, and adding the masses. Substituting the values, 1 kilogram times 6 meters per second plus 3 kilograms times 0 meters per second equals the sum of the two masses times that final speed we're looking for. Then we divide and we find 6 kilogram meter per second divided by 4, there's your 1/4, equals 1.5 meters per second. The results for inelastic collisions are always consistent with the mass ratios that we determined in the first video. Here in the next question, we have a diagram of a block of mass m initially at rest on a frictionless horizontal surface which is struck by a bullet of mass little m moving with a horizontal velocity. What is the velocity of the bullet block system after the bullet embeds itself into the block? So again, this is exactly the same kind of inelastic collision where one body crashes into a second body, they lock together and move off. What's very interesting here is that this is one of those rare questions where they actually ask you for the general solution, which turns out to be choice 4. If you look at this derivation right here, this is exactly what we've been doing every single time we've been calculating for the final velocity in the inelastic collision. Recall this derivation from our last video. This answer is exactly what they were looking for in the multiple choice. And here in this next example, we're going to have an inelastic collision where the cars lock together, except this is the first time you're observing that one of the cars is not at rest. In fact, both cars are moving, and not only are they moving, but they are moving towards each other. This is a head-on collision. Let's see how we're going to solve this problem. Even though we're still going to use the conservation of momentum, momentum before equals momentum after m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime, we still should look at the scenario and use our intuition. We have a lighter car moving to the right at 3 meters per second, and we have a heavier car moving to the left at the same 3 meters per second. We should get the sense that the heavier car is going to win in this contest. Let's take a look at the math and see if we're right. Starting with the law of conservation, and we know that it is an inelastic collision. We know that the momentum before must equal the momentum after. However, the final speed of both cars is the same. Since v1 prime equals v2 prime, we make that equal to vf. We know that the vf factors out and we take the sum of the masses in the after expression. Now let's see how the values go into the expression. Making 4 kilogram mass 1 and making the 6 kilograms mass 2, we need to account for the velocities. 4 kilograms is moving to the right 3 meters per second. That's a positive value. So 4 kilograms times 3 meters per second plus the 6 kilograms times negative 3 meters per second. This is a very important distinction because this negative implies that you are moving to the left. And if you leave out the negative, then of course you're going to be moving in the wrong direction and you're going to have the wrong final velocity as your result. On the right side of the equation, we take the sum of the two masses, 4 kilograms plus 6 kilograms multiplied by that common final velocity. And of course, when we solve this, we get 12 kilogram meters per second minus 18 kilogram meter per second equals 10 kilograms times an unknown VF number of meters per second. Then when we simplify and divide, we find that the final speed is actually equal to negative 0.6 meters per second. The negative implies west, and the 0.6 meters per second is the speed of the group as they travel to the left, which is the west in this picture. And there you have it. Here were some examples of the inelastic collision utilizing the conservation of momentum. We also did some problems where both of the cars were moving and not even in the same direction. So you can see the universal applicability of this expression. I hope you enjoyed this video, and I thank you for watching. I'll see you in the next video, where we will be working on the conservation of momentum applied to elastic collisions. See you there.